This is the Building Automation Monthly Podcast with Phil Zito, episode 169. Hey folks, Phil Zito here, and welcome to episode 169 of the Building Automation Monthly Podcast. In this episode, we will be continuing our multi-part series on HVAC control. In this episode, we will be discussing hot water systems. So we're going to take a look at some of the fundamentals of hot water systems. Then we are going to go through hot water boilers. We're going to talk about multiple boiler control, and we're going to kind of close it out with steam and heat exchangers, things like that. So if you haven't listened to the past several episodes, I definitely encourage you to listen to them. I think it started at episode 166, I believe, where we talked about space control. Then 167 was airside control. 168 was chilled water control. And this episode is obviously hot water control. And this episode is sponsored by our Control Sequence Fundamentals course. I highly encourage you to enroll in this course if you are someone who is trying to learn how HVAC control sequences work. Maybe you're a designer, maybe you're a programmer, maybe you're a technician or an engineer, and your responsibility is not necessarily as an HVAC mechanic, but you need to understand HVAC in order to do your programming, commissioning, startup, installation, and design. This course will take you through control sequences in great depth. We're going to dive into specifications, go through those specifications, and really pick apart how do you control these pieces of equipment, what process variables, set points do you need, how does the sequence logic flow. It's all there inside this fully online, on-demand course. And when you enroll in it, you have lifetime access to the course. So it becomes your repository of knowledge where you can refer back to the subject matter as you are involved in your day-to-day job. There is no other course like this in the market, and I really encourage you to check out that course. You can find out more about it at buildingautomationmonthly.com/169. Scroll down to the Control Sequence Fundamentals logo, click on that, and you'll be able to watch a sample video, read the course syllabus, and you'll see some of the student testimonials of their feedback on what they've taken from the course. All right, so with that being said, let's dive in to hot water systems. Now, I know this episode is a little bit late if you're listening to it when it drops live. Summer tends to do that for me. I get involved in a lot of activities with my kids, and things just tend to fall by the wayside at times when it comes to recording the podcast episodes. So, that being said, got time now, gonna fully get focused on this episode, and we're gonna take a ton. So here's kind of the mindset I want to put you into as we're approaching this, right? So in the previous episode, we talked about chilled water, and we talked about how we're taking heat out of the building with chilled water systems. If you grasp one thing with chilled water systems, it is that it is a transfer of heat from the building out into the atmosphere, right? We're taking BTUs. Now with hot water, we're doing the reverse. Now with hot water systems, we need to inject heat into the building. Typically, we're going to go and use some form of combustion to create a heat source that is then going to heat up water. And then that water, using the piping system, which we'll cover in the next episode, is then distributed throughout the building and is let into the airstream, let into the building environment via, radiators, via hot water coils. There's a variety of different ways that heat can be basically injected into the building. But remember, if you get this, I've tend to find that throughout my career, if you really understand just the simple relationship of we're either transferring BTUs out of the building or we're transferring BTUs into the building, if you understand those, it really helps you to troubleshoot a lot of system failures. So with that mindset in your head now, let's go and approach a lot of basic hot water concepts, and then let's dive through our different hot water systems. So at first, what are hot water systems, right? I mean, what are they? They're one of the main ways that heat is moved around a building or a campus. Now, I said one of the main ways because you do have electric heat, right? You do have gas heat. But if we're talking about campus-wide systems, if we're talking about large environments that require large amounts of heat, water is an amazingly efficient transfer agent for that energy, because heat is nothing more than energy, right? It's BTUs specifically, and there's several fundamentals that we need to understand in order to grasp why heat is nothing more than energy and why water is an amazingly efficient transfer agent for that energy. So you're going to hear me utilize several terms throughout this episode, and I just want to make sure we're grounded on them because they can sound interchangeable, and in some cases they are, in some cases they're not. So heat is a form of energy, and this energy is measured by British thermal units, also known as BTUs. Now, BTU, quite simply, is the amount of heat or energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So why does that matter? Why water? Well, like I said, water is a very efficient heat transfer mechanism. You see, in order for BTUs to go and transfer, they have to be contained in some form of element. And the typical elements we have are air, water, and steam. Now, steam, high pressure steam is the most efficient because as you pressurize steam, you can have more BTUs per pound. And with pressurization, you can have more pounds of steam. And air is the least efficient just due to how it contains air, or how air contains air. No, how air contains heat. The thing is, though, because naturally folks are going to be like, well, why don't we use high pressure steam all the freaking time if it's so efficient? Well, one, it's corrosive. Two, it requires special equipment, pipings, valves, condensate drains, etc. Now, water, it's a great medium. It's not as efficient as high pressure steam, but it's more efficient than air, and it provides a way for us to do heat transfer without the negatives of steam. Now, definitely steam has a place, and we'll talk about that later in this episode. So where do boilers come into play? Why do we use hot water boilers? Well, boilers heat up water or steam by transferring BTUs from a fuel source into the water or steam. Now, usually this is done through combusting some form of fuel source like fuel, gas, coal, or wood. Sometimes it's done with electricity. You see these on smaller boilers typically. So boilers, what they do is they provide hot water to a loop, typically a primary loop. Once again, we'll be talking about piping and loops and all that jazz in the next episode. But boilers are supplying this hot water to a loop, which then supplies the hot water to coils, which then transfer heat from the coil to the air, thus providing the heat. But there's several constraints we need to be aware of when we're controlling boilers, and typically in our control sequences course, I teach boilers before I teach chillers, but being that the time I'm recording this, it's summertime, that's why I taught chillers before. But typically I teach boilers first because if you understand boilers, there's several knowledge points that transfer over to chilled water systems and several that don't. But let's kind of talk about what a boiler is, right? So a boiler has typically tubes inside it. It has some burner that regulates fuel, and it has an exhaust that regulates the actual exhaust of the air. It has an air intake that regulates the oxygen, and it also will have piping and valves, and it has a lot of different moving parts and pieces. But as a controls person, we are typically focused on one of two things, right? So we're either focused on simply enabling the boiler and maybe sending a 0 to 135 ohm resistance signal to the burner control to control our fire rate or temperature reset. So that's one way. Or we're taking a more inclusive approach to controlling it, where we're actually concerned about the flue and the oxygen percentage, and we're concerned about the dampers in the room that the boiler's in, so it has an oxygen feed and so it has an exhaust and all that. I will tell you though, in the majority of my experience, we are just simply sending an enable and doing burner control. And that is allowing us to reset the hot water supply temp based on controlling the fire rate of the boiler. Now, here's the constraints when we're working with a boiler. Now, I know some of you are going to be like, well, Phil, this isn't true with certain types of boilers. This is true with the majority of boilers. So just realize that there are some types of boilers where some of this is not necessarily true. So with boilers, you have to maintain a minimum outlet temperature, and you have a minimum outlet temperature, you have a maximum outlet temperature as well, right? And the reason you can't go below the minimum is that you don't want to go and condense, and the reason you can't go above the maximum is because you'll start to do boiling and things like that. Temperature drop needs to be maintained across the supply and the return. You don't want to have a huge temperature differential between supply and return that can actually be bad. And when you turn on boilers, you typically need to slowly warm them up, and this will tend to affect secondary control, morning warm up, and multiple boiler setups. So when you're approaching that, right? When you're approaching boilers, it's not like a chiller where you just turn it on and it starts to run. You typically have boilers that will go into low fire, then they'll go into high fire, and they'll start to just gradually warm up. Otherwise, you shock the system. And the thing is also that when you're dealing with hot water temperatures, if you have a primary secondary loop, you want to primarily manage the hot water temperatures in the secondary loop via the piping and valves and not via the boiler control. Ideally, the most efficient way is to maintain a temperature on the hot water boiler based off outdoor air temp, so that way you can kind of calculate. Now, you can look at valves and things like that to calculate BTU load, but outdoor air temp also gives you a pretty good idea of what your BTU load is, and then you reset your hot water supply, and your hot water supply then goes, and what's going on with that is then you have a mixing valve that then allows hot water out to the secondary loop, and the secondary loop is a demand-based loop. So it will pull BTUs from the primary loop depending on how much you actually need it. And last thing you want to realize about boilers is that lead lag is different than chillers. All right. Now, with chillers, we just simply switch over. We call it a day. With lead lag, since we have slow warm up and low fire rate and high fire rate, the amount of time to switch from one boiler to another is a little bit longer depending on the boiler. All right. So with that being said, we've got some core concepts down, right? Let's take a look at just a single hot water boiler. How are we going to control this simple machine? And I know simple is a relative term, but how are we going to control it? Well, when it comes to pretty much any boiler, we are going to need really three things: flow, fuel or power, and control. All right. So flow is critical. Without flow, we can damage systems. Now, with chillers, most of the time, as well as with boilers, most of the time, they're going to have a flow switch. And if you don't have flow, it's not going to start. It's not going to run. But I've seen some weird stuff in the field, people jumping flow switches and all sorts of craziness. I don't know why. Don't do that. But you can really damage stuff. And with boilers, more so than chillers, you can really damage stuff when you don't have flow. So that's why we want to make sure that we have our ISO valves open. That's why we want to make sure that we have our pumps running. That's why we want to make sure we have flow to the boiler. Now, as far as fuel goes, typically you're going to have very little to do with fuel except for maybe adjusting fire rate via a resistor or 0 to 10 or 4 to 20 signal, sometimes via MSTP or backnet signal, which, by the way, I really recommend when you're controlling boilers that you hardwire things. It's just much easier to troubleshoot versus using, hey, we've got a Modbus or a backnet interface to the boiler. It's just a lot easier to put your meter on a 2-pair and say, hey, these 2 conductors, I'm metering them. They have 2 volts DC, whatever, or they don't, versus trying to figure out what's going on with MSTP, especially with a system where it's responsible for the heat of the entire building. Now, you do need to understand fuel and its relationship to the boiler, and kind of here's why. I was working on a hospital. It wasn't really a hospital. It was an inpatient treatment facility for elderly folks. And the boilers just weren't working. The building kept getting cold. And this was in Dallas at the time. And we were under a really big cold snap. To make a long story short, what ended up happening was so many folks in the city were using gas that the gas pressure had dropped just enough that the boiler could fire, but it couldn't reach the heat production that it needed to. And so we kept trying to figure out, why are these boilers not producing heat? Why are they not producing heat? And finally, a tech I was with noticed the pressure gauge and was like, that doesn't look right. And sure enough, we weren't getting gas pressure. So that was causing the heat to not reach the level it needed to be. And if you've ever been in a building where you're on design days where it's either at the coldest it's designed to be or beyond that, or at the hottest it's designed to handle or beyond that, I'm talking outdoor ambient, then you know that as you start to slip in those scenarios, meaning that you're not able to keep up with the heating or cooling, it's a cascading effect. It just keeps getting colder and colder because you're not able to enter enough BTUs, and the rate of BTUs leaving or entering the building is faster than your ability to remove or replace them. So obviously I'm talking about cooling is where you're removing BTUs and heating is where you're replacing and adding BTUs. So understanding fuel is really important. And then finally, there's control. Now, when we control boilers, we're primarily focused on our boiler enable, our hot water pump command, any ISO valves if they are present, and our hot water supply set point. So boiler enables pretty simple. 9 times out of 10, you're going to use a RIB U1C, and you're going to connect it to the outside of the boiler control module and wire it to the contacts on the control board. Now, hot water pump command, this is really basic. You're just going to go and turn on the pump either at the motor control panel or at the pump itself. And a flow switch typically built into the boiler will trigger and will allow the boiler to start its heating sequence. And finally, hot water supply set point. So there's kind of 3 ways you can do this. There's control the fire rate of the boiler. This is the most common, but it's also the one I don't recommend because it's for newer techs. It's the one that's most difficult to figure out, especially if you're working with resistors and you don't have a simple 0 to 10 volt interface. You can control the set point via 2-wire control if it supports that. If the control panel supports that, that is my recommended method. And then a lot of newer boilers have interface cards, so you could use backnet or LAN or Modbus. So hot water supply set point is our primary variable that we are controlling. And ideally we want to control it to anywhere from 160 to 200 degree hot water. And then we mix that into a secondary loop that resets anywhere from 140 to 160, just depending on demand. Typically you'll just figure out where you want to control that. 140 is a very common number. Now, if you don't have a secondary loop, you can reset your hot water supply temp, and you can do that via an outdoor air reset. The only thing, once again, is to be cognizant that you don't have a huge delta between your supply and return, due to the damage that can cause, as well as not dropping below your minimum or going above your maximum supply temperature ranges. Then you have mixing valves, right? So mixing valves, as I mentioned, they are going to reset temperatures. They're going to look at your supply temperature on your secondary loop and reset that. Sometimes that supply temperature set point is calculated based on what's the word I'm looking for here? Just a reset based on valve position or calculated BTU load. So it's really simple, right? Hot water boilers, we get our hot water supply and return temps, our primary pump command and status. We want to make sure we have flow. We enable the boiler. So we enable the boiler, we turn on the pump, make sure we have flow, and then control our hot water supply set point. That's pretty much all there is to it when it comes to single boiler control. Now, what if you have multiple hot boilers? Well, in this scenario, when you have multiple hot boilers, you kind of have three strategies, and those are Unison Control, Staged Control, and Lead Lag Control. So Unison Control is one of my favorite controls, as long as the boilers are all sized the same, and you control them, basically running them all at the same time, and you fire the same fire rate or same temperature set point across multiple boilers. Now, like I said, this assumes that the boilers are the same size and that you have the same flow rate through the boilers. Now, there is a hybrid version of this where they're set to maintain a supply set point, and then they vary their own firing rate based on the supply temp. And this can be used when boilers are inside or are different sizes, different capabilities of heat production. But this is Unison Control. It's one of my favorite controls. It's very simple to do. It also enables you to just have kind of a precise control, because you don't have to worry about different temperatures mixing. You don't have to worry about bringing on a second boiler. But once again, you are running multiple boilers, and you do reach a efficiency curve where when you're on the low demand side, it's definitely less efficient than staging on and off boilers. Staged control is where you stage on boilers, right? And as the temperature goes and drops below the hot water set point, more boilers are brought out of low flow or low fire mode and are brought into control. So these boilers are running maybe in low fire, or maybe they're completely off, which is not recommended. And then they start to fire more, start to heat up more based on when the supply temperature drops below. Now, staging has a lot of nuances to it. You got to get your timing right. You have to understand the impact of when you stage on and stage off multiple boilers. This can provide more efficient control in low load scenarios because you're able to really trim down your production of heat. Whereas with the Unison Control, you only have so much you can trim down that heat production. And then finally, lead lag. This is a less common sequence in hot water. Basically, it's where you have two boilers and you rotate based on runtime and lead boiler state. So if the lead boiler fails, you switch over to the lag, and if the lag goes, then you're kind of screwed, right? But this is something I just don't see this as much. I see staged quite a bit, and I see Unison quite a bit. Now, there are two forms of lead lag, right? So you've got lead lag, that is just pure lead lag. Each boiler is sized to handle the building, and you switch over. Or you have lead lag with lag acting as a peak load conditioning device. And you'll see this in chillers too, where lead will handle 80% and then lag will kick in for that last 20%, as well as any demand above your design days. So you'll see this in critical environments where they absolutely cannot tolerate not having the environmental conditions they need, especially healthcare, data centers, etc., where the cost of having an oversized system is less than the cost of not being able to do their business operations, or the impact of life safety, especially in healthcare environments. So from there, right? So right there, we've got boilers, we've talked about them, we understand all the concepts. Now we come into this thing called steam. Now, steam is really bad, and it's really good at the same time. You know, I've seen invisible steam leaks cut through broomsticks. I mean, that's kind of one of the things you do as you're walking around trying to figure out, oh man, is there a steam leak? You walk around with a broom and you can swipe it and steam will cut through that. I've seen people get burnt by their hand just getting close to an uninsulated steam pipe. Steam can really hurt you. At the same time, it is one of the most efficient ways to transfer heat energy throughout a campus. Basically what steam is it's a phase change from liquid water to gas. So a phase change, right? This is a state of matter. So there's, solid, liquid, gas, right? And when you change phases, it requires a lot of energy to do a phase change. So consider that to go from 32 degree water to 212 degree water is 180 BTUs. But to go from 212 degree water to the same 212 degree steam is 970 BTUs. Yes, that is more than 4 times the amount of energy to change state from 212 degree water to 212 degree steam. So that is why steam is used on large campuses, because you have 970 BTUs packed into that 1 pound of steam. So then when you pressurize steam, you can see that you've got a lot of energy within that steam. Now, there are 2 types of steam, right? You've got dry steam, which contains the most latent heat for proper heat transfer, right? It's not got a lot of sensible heat, which is bad, because we will typically use heat exchangers in order to transfer heat from a boiler into, or from a steam loop into a hot water loop. So typically you'll have a steam loop that runs around the campus, and you'll have these heat exchangers, and these heat exchangers will sit in the building, and the building will then allow you to transfer heat from the steam side to the hot water side via the heat exchanger, and that then acts as your quote hot water boiler for that building. Now, wet steam is bad. We want to avoid that because that does not allow us to transfer the latent heat that we need as effectively, because wet steam has more sensible heat in it. It's got more moisture in it. It just makes it less efficient. We have to deal with condensate, all sorts of stuff. So then low pressure, right? That is what ideally we want to focus on. We want pressure that's just high enough to overcome the system resistance, meaning the resistance of pushing all the steam throughout the campus. And high pressure is what we want to avoid, because high pressure is typically used for steam turbines, for anything that's energized by steam. It is not used for heating. So heat transfer, we use kind of 2 ways of transferring heat from steam. Directly utilizing coils called 1/3 and 2/3 coils in a air handling unit. These are large air handling units, maybe 100% outdoor air in environments that have low ambient conditions, and we fire the 1/3 first, and then the 2/3 coil second. So that's 1/3 of the capacity and then 2/3 of the capacity. So with steam, due to pressurization, you're going to get a lot of heat within that first 1/3. And so what happens is we fire that 1/3 coil. It has its own actuator, typically a pneumatic actuator on it. We will gradually open that up, and that will really give us a spike of heat. And then once we've fully actuated that, we can then fire our 2/3. In some sequences, you'll actually fire your 1/3, then you'll close your 1/3, you'll open your 2/3, and then if your 2/3 isn't cutting it, then you'll open back up your 1/3. So I know, really confusing, but if you've messed around with steam coils and air handlers, that makes complete sense. If not, just make sure you kind of study this, because it's a little funky as far as sequencing. You definitely want a very slow acting PID loop, and you want to get as accurate with your pressure control of those pneumatic actuators as possible. And then finally, as I mentioned, you have tubular heat exchangers. Notice this is not a plate heat exchanger. They can be used, but they typically have constraints mainly around pressure drops, whereas tubular heat exchangers tend to work quite well with steam. And then there's a little bit more around steam with tubular heat exchangers, but I'm not really going to cover it because we're at the 30-minute mark. I just looked over. I'm like, holy crap, we're at the 30-minute mark. Now with steam, last thing I kind of want to leave you with here is the two strategies for 1/3 and 2/3 control and what condensate is. So with 1/3 and 2/3 control, you have the scaling strategy, right? You implement a single process loop, and this single process loop then has scalar objects. We're talking about the programmatic side, right? So actually inside the controller programming. So you have a single PID loop that drives off of whatever temperature you're driving off of, typically discharge air. And then you go and you drive your 1/3, 2/3 valves scaled off of this. Or you can have a separate loop strategy where you have 1/3 loop that is controlled and a 2/3 loops that controlled, right? So the second loop is enabled when the first loop is at 100% for a certain amount of time. Then that first loop will go down and start to close itself down. The second third will start to open itself up, and then the 1/3 will open itself up again. Now, this strategy is difficult to control. It can lead to loop windup. I don't recommend it. I recommend the scaling strategy. That tends to work well. If you are going to use a separate loop strategy, you really have to pay attention to your PID loop tuning. You also have to pay attention to make sure that you're shutting down that 1/3 loop prior to enabling that 2/3 loop, and then bringing that 1/3 loop back on if needed. And finally, condensate. So whenever you transfer steam, whenever you transfer heat from steam, you have a phase change that causes it to condense back into its liquid form. This is natural. It's okay, but it needs to be controlled. You have to remove the condensate from the piping, and you typically will do that using a condensate pump at the bottom of the coil or at the heat exchanger. This will remove that condensate, and it will make sure that you don't have condensate buildup, which will lead to wet steam, which will lead to bad heat exchange, which is just all corrosive and all sorts of bad stuff, right? So with that being said, you now have a pretty solid primer on hot water systems. Now, granted, this was only 30 minutes, and I think in our course we spend about 4.5, 5 hours on this. So if you are trying to learn more about HVAC, I really encourage you to check out our Control Sequence Fundamentals course, and you can find out anything note-wise that we discussed, as well as links to the previous episodes at buildingautomationmonthly.com/169. Thank you so much for listening to this episode. Definitely appreciate your feedback, comments, questions, and I look forward to talking to you in next week's episode, where we will be discussing piping and pumping. So thanks a ton, and until next week, take care.